Okay, so in this part, what we are going to look into is that a little bit technical details, that how the radio imaging is actually done. Okay, so this is not as straightforward as in optical astronomy. So we'll try to take a look the mathematical formulation, and from there how it goes to the concept of data. I mean, in radio astronomy, I have we have given you the data, right? You guys have downloaded. Everybody has downloaded, right? Right? It's a good amount of data. What this data means? Everything is data, right? So that we'll try to make sense of it. What do we mean by this data, and how and what information it holds from the sky. Okay. So yeah. So I mean, typically, when we talk about imaging, let's say, right? I mean, what it comes to our mind. So imaging, it's like, what is an image? Image is a kind of representation of an object in a two-dimensional plane. Let's say if it is a 2D image, correct? So you have X versus Y, and at each X and Y point, you might have intensity, you might have color. So it's basically representing your actual object, right? So if you look at this pinhole camera, so you have an object over here, and you are forming a kind of image of that same object in the screen, right? Now this is with a pinhole camera, but if you have a telescope, let's say optical telescope, how it does? You have a primary mirror, the rays are coming from infinity. Let's say I have a point source somewhere over here at very far, let's say here. Now from this point source, parallel rays, because it is very far, these rays will be parallel, right? Now these parallel rays comes here, hit this parabolic mirror. So one set of rays is coming there, it will go back, try to meet at focus, but if you have a secondary, it will go and meet over here. So it means this point source is being reproduced over here, right? So this will be an image of the point source which is sitting at infinity somewhere, right? And then if you look at let's say our mobile phone, right? Our mobile phone has camera, correct? And then it has some CCD, right? You guys are familiar with these terminologies, right? How many megapixel of your camera? So what do you mean by that megapixel? Any idea? 10 megapixel means what? 10 to the power 6, 10 to the power 7, right? 10 megapixel is 10 to the power 7. So it means that in this focal plane, you are putting a chip, right? Which has like 10 to the power 7 pixel points, and you have 2 points near side. So this guy will be, form an image at different pixel, and here it will be a different pixel. Now think of it, if this pixel is a big one, like let's say only 1 pixel. Now 2 points over here, 1 point here, 1 point here. So that will make 2 points over here and here. Now they will sit in the same pixel, right? So you will not see these are like 2 points. You will see just 1 point because your pixel is this big. So it means more the resolution means more megapixel is like better quality of the image, because each individual point you are resolving it, differently, right? So, so the resolution of a telescope is lambda by d, of the order of lambda by d, right? So for optical case, what is the lambda typically? Optical wavelength का lambda कितना है? Sorry? Thousands? 4,000 to 400 to 600, 400 to 700 nanometers, right? It's about 0.4 micron, right? 0.4 to 0.7 micron. Let's say 1 micron, right? So now, if you want to place in the focal plane, right? How many megapixel? 10 to the power 7. Now x into y is equal to 10 to the power 7, right? So in x direction, how many will be there? About 1,000. 1,000 into 1,000 in 10 to the power 6. So 1,000 pixel, and each pixel is, let's say, 1 micron, correct? If we go by this, lambda by d, forget about d, let's say some number, order of lambda. So if I say that, this resolution is about 1 micron and I have 1000 pixels to place, right? So this will be like 1000 into 1 micron, 10 to the power minus 3, that's about a millimeter, right? So your whole chip will be like an millimeter. Within that you have to make like 1 micron or so, right? Fantastic, right? This, remember this thing, we will come back. Now, if we look at our eye, right? Eye is like few millimeter diameter, right? 1 centimeter, a few millimeter diameter. So the resolution, sorry, yeah. So this this resolution lambda by d, okay, because this lambda is like in micron, in optical case it will be like very very high in a sense, because this number is very small, correct? Now, if you look at lambda of radio wavelengths, let's say, so radio wavelength is in meters, right? This is this big, correct? Now micron to meter is already like 10 to the power 6 times, correct? 1 micron we were talking about, and now this is in meter, so this is already 10 to the power 6 times. Now if you have to produce the same resolution, correct? Let's say I had a D here, it is 1 meter, correct? I get some resolution of order of lambda. Now my lambda has been increased by 10 to the power 6 times because I have moved to radio, right? Then to keep the same resolution, I have to increase this D diameter also by 10 to the power 6 times. Now if we are talking about a optical telescope of diameter 1 meter, to match the same resolution, I have to have a radio telescope which has a diameter of 10 to the power 6 meters. What do you mean by 10 to the power 6 meters? 1000 kilometers, right? So that's a big deal, right? So this, this is for a comparison, that resolution of a 100-meter telescope, okay, like Effelsberg telescope, which has the same resolution like your eye, few millimeter diameter, right? But there is necessity to go at high resolution at radio wavelengths. So as we have, like we were discussing, right? I have shown you this Cygnus A image where, like, there is a central black hole system and there is a jet which is coming out, right? Now to look at that central part, the central part is very compact. Like in this Event Horizon Telescope also, right? That, black hole things. So these are like very compact, it's very high resolution you require, right? And that is actually possible. Those kind of high resolution is possible by doing something called very baseline, very long baseline interferometry, okay, VLBI, right? And the concept is very similar. So here, what I'm trying to show is that you see that I have a telescope, right? This is kind of a solid disk, right? Now, many of you have seen optical telescope, right? You guys have seen optical telescope. Remember, in the optical telescope, in the front, you have this secondary mirror, right? You have this primary mirror, and this secondary mirror is actually from the spider. You have this something hanging over here, right? Which is actually pushing the light over here, and then it is going through the eyepiece and you are seeing it. Now tell me, this is my primary mirror. This part, it is blocking the light. But does it make any difference in the image? No, right? You are not seeing the moon like, in parts. You are seeing the moon in full thing, right? So try this out. Even if you keep your hands in front of the optical telescope, it will not make the image different. It will only dim the image a little bit because you are blocking the light. So what I'm trying to say is that if you go in this image here, you see, even if you block this half, let's say I am blocking the bottom half, right? Still these rays will go reflect here and form an image over here. It means that if you have a telescope and let's say at some part of the telescope is broken, right? It will still collect those rays coming from this and this. Maybe here is gap, but this, and it will form an image. Now, because of the broken parts, you will not be able to collect all the lights, but that is okay, right? It would be a little bit dimmer. It will not be as bright, right? But you will still be able to form the image. Now, this is a very interesting concept. Similarly, now if I talk about, as I said, that if you have to match the resolution in the radio wavelength, you have to make a big telescope, correct? Now, this big telescope might have gaps. That is okay, right? I'll still be able to form the image. May not be have that much sensitivity, right? I might lose some sensitivity, but in principle, I can do that. So here I am showing that, I have a large telescope, right? Which has, gaps in between, some parts are not there in a sense, okay? But I will still be able to form the image and kind of, produce an image, right? So this is like in a traditional way. So basically, I mean, these right rays are coming and I am just adding them in phase. Correct. How the image is being formed. Let's say from here, you have one rays come, it get reflected and come here. One rays get reflected and come here. And this is a parabola, right? What is the kind of property of a parabola? That if you have this line of directrix, so any line coming from perpendicular coming in here, so they will all have the same length, right? So this plus this plus this plus this, they are same. It means all the lights are traveling same optical path, correct? And when they travel the same optical path, this is a parallel wave front. It means the phase of the light is same over here. So when they come and meet over here, so they will all come and meet in phase, correct? So now this analogy will come again in the later part. Okay, I will tell you, right? So now what I'm trying to say is that if this is the case, that you can have a big telescope, but most of the part can be empty. I am again telling that I am compromising on the sensitivity, but I will be still able to make an image. So now similar concept is applied over here when I make a big array like VLA, very large array. So you see the telescopes are like, individual elements are here, 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 and here. So they are like, you can consider them like, part of the telescope, which is distributed, and they can make a big telescope, but most of the part is empty. That is okay. So if you can combine the signal received by these telescope in a clever way such that it can, make an image, so you can still produce an image which will have a resolution of like, from here to here, this big. So now you had to start with, if you have a single disk telescope, like you had the resolution theta was lambda by d, when the d was the diameter of the telescope. Now I am building an equivalent telescope by distributing my elements over a large area. Now my resolution will be lambda by this capital D, which is basically lambda by b, which is basically baseline length, which is coming from here to here. Now this is at conceptual level is okay. You guys can accept this, right? Okay. So the mathematics we will do. So this is called interferometry. Okay. This is called interferometry, and this is very much similar to kind of two element double slit experiment. So we call two element interferometer. So if you have like one element over here, another element over here, so you can do interferometry between these two, and this is very similar to what is double slit experiment, right? So double slit, you people have done this thing, and almost everybody, I am assuming that familiar with it. So you have parallel wave fronts are coming. You have two slits, one is over here, one is over here. Then these can be considered as the source of secondary wave fronts, which come over here and they kind of add in phases, right? And then you have this interferometric pattern, dark and bright spots, right? Fantastic, right? So you actually be able to, if I ask you this question that this is one bright then dark, right? Another bright and dark. This is like pattern from one slit, right? Now let's say I have one point over here. Have you guys done this experiment in lab? How many of you have done this experiment in lab? Many of you have done, right? So we used to have like one slit, one illuminator like this sodium lamp, where there will be one slit, and here there will be two slits, right? Now assumption is that this one slit which is over here, this is producing radiation, which is like in a spherical wavefront and coming as a parallel wavefront, which is like this, correct? This is fine. Now let's say I have one source over here. Now you can consider it like a star. Let's say I have a star somewhere over here, right? Now if I have a star very far, it is a point source, right? Point source emit spherical wavefront. Now if they travel far enough, they will be parallel, correct? Fantastic. So they will produce, let's say if I have two slits, they will produce bright, dark interference pattern, right? Now I have another star which is like nearby. So I have one star. I have one star here. So this will give me parallel wavefront like this, right? Now I have some another star here, right? Now this will emit a wavefront like this. So this will also give a parallel wavefront, but there will be little bit of angle. Yes, agree? If I shift this guy to here with respect to this plane, there it will create a little bit of angle. Yeah, agree? Fantastic. Now that star will also create a pattern of this sort. Dark, bright. Because see, this is a point source. So I have a series of parallel wavefront. They will go and do a, interfere and make a pattern of interference pattern like this, right? Then I have another star over here, which will also make a pattern, but that pattern will be a little bit shifted because there is an angle, correct? Agree? Now, think of a situation that these 2 points, this one and these points, they are very close, let's say, very close, right? So these black and white pattern, and then the pattern 2, which is another black, so there will also be very little bit of shift, very marginal shift. You will not be able to figure out whether there are 2 stars or 1 star just looking at the pattern, because this is bright dark only, but a little bit widen, because there is a little bit shift and this will be a little bit widen. That's about it. So it will be very difficult to tell, for you to conclude that wahan pe there is 1 star or there are 2 stars. Now think of a situation, I make this star far apart. So now I have 2 patterns. One was like very close, one top of each other, right? Now because that star is a little bit further, this pattern actually separates out. How? The black and the dark, they overlap. Means one bright, iska dark, they overlap. Now in that case, the pattern will be completely kind of smoothened out. Now you cannot say that I have 1 star, because 1 star will make bright dark, right? So it means that if you have 2 guys sitting over there, right, you will be able to tell that what is the theta you shift, these 2 pattern matches with each other, right? Now if these patterns are like very broad, let's say this much big, each white and each bright and dark is like this much big, then I have to move this star actually very far away to make like bright and the dark alternative to sit together, right, to wash out this thing. But if these patterns are very fine, let's say very fine, sharp, bright and dark, then a little bit shift will shift this thing and you will be able to figure out there are 2 stars, correct? Now what makes these patterns broad or narrow? That is the distance between these 2 slits, right? You guys all agree with me that if these patterns, bright and dark patterns, if they are narrow, it is easily you will be able to tell there are two stars, right? So this is the concept of resolution. Means, what do I mean by resolution? I can resolve these two guys. I can resolve means I can tell that there are two guys instead of one, right? That I am being able to resolve these two, right? Now, if I am being able to resolve these two, it means that if these patterns are sharp, right? If they are sharp, it means I can resolve finer details. It means even though stars are nearby, I can say that, oh no, there are two, not one, right? So to make these guys sharper means if this pattern is like this thickness, if you want to reduce this thickness, you need to move these slits far apart. If you keep the slits close, they will be big, this pattern width will be big, larger, right? If you make these slits further, this will be sharper and the resolution will be high. Now, does it make sense here? You see, if these two guys, here look at this theta, lambda by b, right? What is b? B is basically distance between two slits or two elements, right? If these two guys are closer, this b is small, your resolution is small. It means whatever this pattern is coming, you will not be able to very, very detailed, you cannot say that, okay, there are two stars. But move this guy, one guy here, another guy here, this b increases. It means I am putting my slits far apart, right? Now my resolution, that how I can resolve this two star better, that will increase because my pattern width has decreased and this b is increased, right? So now, does it make sense? So it is equivalent to a double slit experiment, and you can actually work out and show that this delta theta is basically nothing but this width of this pattern. Okay, you can mathematically work it out, and which is basically lambda by b, where this b is basically distance between these two slits, right? Okay, so all right, so I will actually skip this part. I will directly go to Van-Sitter-Zernike theorem. Okay. All right. So so now you can see that the antenna basically what we say two-element interferometer. Okay. So they are kind of equivalent to your double slit experiment. See, if you think in a broad way, what is interference? Two waves are coming and they are kind of adding in phase, correct? Now I can do the same thing in computer. I have one telescope over here, another telescope over here, right? And what is coming from the sky? Coming from the sky is electromagnetic radiation, right? And this electromagnetic radiation, you can write it down a cos of omega t plus phi, right? Let's say this is, electromagnetic radiation is coming. Electromagnetic radiation is what? It is basically electric field, electric and magnetic field, right? Electromagnetic radiation is electric and magnetic field, right? You guys don't agree with me, right? And this electric field, if you have a conductor, what it will do? It will induce a current, right? Now electric field will try to move the electron, right? It will create a current. This current you are tapping. You are bringing this current and recording that basically that current, and that current is I is equal to what? V by R, voltage, right? V is equal to IR. So now this current is basically this V is coming, this is coming from that electric field, right? This is what you are measuring, and this electric field has a nature A cos of omega t plus phi. So your current also, so if this is A cos of omega t plus phi, electric field is A cos omega t plus phi, this voltage will be A cos of omega t plus phi, with some multiplicative constant, then this current will also be like A cos of omega t plus phi. That is what you are recording, right? Now think of it, each antenna is recording this A cos of omega t plus phi. Other antenna will record some A2 cos of omega t plus some phi 2. Can't you bring it to your computer and do an interference? You can do, right? So it is effectively like the double slit experiment. Instead, you are doing that in a real space, but here you are doing it in computer. That's perfectly fine. It's equivalent. Okay. So there should not be any problem. Okay. So now this is a very important thing. I'll try to quickly wrap this up. And this is basically what I call the foundation of radio interferometric imaging. If you remove this theorem, the whole radio astronomy will collapse. Not the single disk one, but the interferometric imaging will just vanish. Okay. Okay. So be with me. Okay. We'll go slow. If you understand this thing, then you will actually get it, like, you know, what the data, imaging, all these things will actually come very much clear to you. Okay. So be with me. There are some mathematics involved. I have tried as much, you know, I will go through as much as possible. This will take 10 to 15 minutes. So be with me. Okay. So paradigm is this, that I have a source distribution in the sky. What do I mean by source? I have some point which is emitting radiation, correct? Now, radiation means what? Electromagnetic radiation. Electromagnetic radiation, as I said, is basically an oscillating electric field. Yeah. So I have, let's say, this point P1, correct? This point P1, which is on the sky, far away. Okay. This point is far away at x1, y1, z1. And sorry, this is P1 prime, not P1, P1 prime. Okay. So I have a source of some electric field or some electromagnetic radiation, okay, at P1 prime, and I am trying to measure the electric field coming from this guy at some point, let's say on Earth, at point P1, which is x1, y1, z1. These are like Cartesian coordinates. This is clear? Okay. Now, the electric field, as I said, it has an amplitude component and it has a this phase component, correct? Now, electric field, you can also write it as, like, you know, instead of this cos, you can write it in exponential also, right? So E can be written as some A e to the power I omega t minus x. This can be done. Okay. What do I mean by so this part, this omega t part, it is telling you about the oscillation in time. So it means that you have freeze in space. I am not changing my space. I am just standing over here and I just look at the time, tick, 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 tick. Then I will see at some point the electric field is going up. At some point electric field is going down. That is the omega part, right? I can also do the same. I can freeze in time, means I can, you know, align all you guys in 20 places, right? 1, 2, 3, 4, like this 20. And I will say, measure the electric field now and stop. So all the measurement at the same time. But you will see some guy will measure high, some guy will measure low, high, low. So it means it also has a space variation. Even if you freeze in time, it has a space variation. So these are the two variations. Omega t is what is basically time variation, and this kx is basically space variation. Now the time part we will ignore for some time, because when this radiation I am measuring over here, I am going to average in time because the signal is very weak. So I know how this is oscillating in time. That is not my concern as of now. Okay. So we will only deal with the space part. Okay? We will only deal with the space part. Now this, be with me, this electric field E at P1, correct, is electric field at P1 prime here divided by D. Intensity goes as 1 over R square, right? Intensity I, it goes as 1 over R square. And if you have an electric field E, What is intensity? Intensity is proportional to E square. Electric field square is basically intensity. I mean, yeah. Yeah. So now the electric field then will go as 1 over R, right? E will go as square root of I is equal to 1 over R. So if I have some electric field over here, right, and it is kind of isotropically radiating, by the time that radiation reach over here, it is because it is spreading in all 4 pi direction, right? Same thing, you have a point source which is light is emitting, so per unit area the photon will decrease, the power will decrease, right? So if the power is decreasing at 1 over R square, the electric field will decrease as 1 over R, correct? What is the R? R is basically the distance between this guy and this guy, correct? So the electric field you will measure over here is effectively the electric field what used to be at that point, P1 point, right? That is electric field at P1 prime divided by this, right? Divided by the distance between P1 prime and P. This is fine, correct? Now this E I am measuring over point P1 over here. I might have, this P1 prime might not be the only the single point. There might be other sources also. So I have to integrate over all the sources. So the electric field I will measure at this point will have contribution from all the sources. So that is why this integral is coming. Okay, and this is ds1, that is basically integration over the source. This is clear? And this is the amplitude part, and there will be a phase part. So electric field, which is an oscillating electric field, right? What is K? K is equal to 2 pi by lambda, right? K is equal to 2 pi by lambda, right? So tell me, if you go lambda distance, the phase difference is 2 pi, right? So if you go unit distance, this is 2 pi by lambda, correct? If you go d distance, it will be 2 pi by lambda into d. Yes? What is this 2 pi by lambda? It is K. This I am defining that, it is K. It's a definition. K into d, that is what is exactly there, K into d. That is the phase you will accumulate, right? This is the phase part, right? E to the power I theta is equal to cos of theta, right? Plus I sin theta. That theta is basically this theta, that is the phase, correct? So this radiation not only drop its amplitude of the electric field by E by D, it will also have some phase, right? Now this phase is very important actually. We will come back and this will play a very important role, right? So this is clear, everyone, right? Great. Now what I am saying is that this is P1, that is my one antenna. Remember I had two element interferometer. One element here, another element over here. So this is one element I have measured. I will also measure at second element. I have a second antenna, correct? So that will also have the same formalism. The E of P2 prime, this might be some another point in the sky, and divided by E I K, D of P to P prime P2, D of P prime 2 and P2 and DS2 is exactly same, right? Now let us do an operation which is called cross correlation. Cross correlation means just multiply them, multiply these two voltage and add, right? You might ask me why I am doing this, but let's say do it. Trust me, let's do it, okay? And see what happens. Okay, I'll come back to this point. So what I am doing is that I am multiplying these two electric field, that is electric field in antenna 1, electric field at antenna 2. Okay? Multiply and do an average, means summing up them. So then I will have this kind of thing, this E of P prime 2, see from electric field E1, P1, there will be a P1 prime, correct? And this E star of P prime 2, because these voltages are complex, right? They are oscillating, right? So complex multiplication means you have to take a star, it's nothing fancy. So this is E of P1 prime, the E of E star of P of P2. You see here, this is E of P1 prime, So for P1, it is coming E of P1 prime. For E2, you will get E of P2 prime, right? There will be a star. And then you will have this IK 1D for P1 prime P1, and then another D will be P2 prime P2. This is not, I mean, it might look a little bit clumsy, but if you take a look, it is actually not a big deal, right? Now look at this term. This P1 prime and this E2 E star P2 prime. So these are on the source, right? Somewhere there, one point and another point, correct? One star, another star. I am electric field coming from them. I am multiplying and averaging. Now you see, these stars and these stars, they are very far apart. There is no correlation between them, correct? So the electric field coming from one guy and electric field coming from another guy will be completely random, right? They cannot be causally connected, correct? Because I am measuring the electric field at the same time, right? So this part, that electric field from here, if I multiply and average means what? Sometime this is maximum, but sometimes this is minimum, that is maximum, maximum, completely random will be there. So this will go to 0, correct? This part, if P1 prime and P2 prime, if they are not same, if they are different, this part will be 0. So it means this whole integral will only be valid if P1, or only be non-zero if P1 prime and P2 prime are same. Agree? It means this correlation, whatever you are doing, if the correlated signal, that electric field is coming from the same source, then only this correlation is non-zero. If the electric field you are getting is from other sources, two different sources, it will be 0, right? Now, whatever you are getting is actually mix of both. It is from here, and everywhere. Here also it is there, and everywhere. Only the common part will remain if you do this operation, and the other part will go away, right? Fantastic. So I can replace this P1 prime and P2 prime because they are same. So I am replacing this P2 prime by P1 prime. Okay, that is fine, right? Fine. Then what is E of P1 prime and E star of P1 prime? Remember, that is the intensity of that source, right? That electric field square. Electric field square is the intensity, correct? So it means this is basically I of P1 prime. Now you see we are getting somewhere. What is this I? This is the intensity of that source. That is what we want, right? We want to map the sky as a position of, like, intensity as a position of X and Y. We are already have, seen some term over here like that. Okay. So this I P1 prime e to the power I k d, and there this d square and this thing. So this term is fine. Now this is the phase term. Now phase term is basically quite interesting. Now I have replaced the P2 by P1. So P1 prime to P1 and minus P1 prime P2. So effectively I have this point. So this is the distance. This is another distance. Difference between these two distances, that will basically the phase accumulation, right? So this is very similar actually. This guy has traveled this much path. This guy has traveled this much path. So you have to subtract these two paths and just do this exercise, this lambda for 2 pi, and then whatever the difference between these two. So difference between this we have to calculate, okay? Because these are like, oscillating signal, complex number, you cannot actually ignore the phase, okay? So this I'll come to that point, okay? So now let's say I am defining some quantity, let's say from here to here. So this is my antenna, okay? This is my antenna, this is my source, and let's say from here to here, this distance is roughly r, okay? This is just a little bit technical, be with me. And what I'm trying to do is that if I have some coordinate x1 prime, and this is the distance. So x1 prime, if you see, let's say this here. So I am trying to basically, what I'm trying to do is that this distance I am trying to evaluate, okay? Prime is the coordinate in the sky, okay? So x1 prime, that is, some x1 over here, which will be basically r into cos of theta x. So if, let's say, I have, this is my angle, and I have some deflection over here, and this makes it angle theta over here, So that deflection, it will like, S is equal to R theta, correct? And if theta is small, cos theta is equal to theta, correct? So this x1 is equal to, you can write R of cos of theta x. Similarly, y1 prime, you can write R of cos of theta y, and z R of cos of theta z. Now I am just defining that, cos of theta x is equal to L, cos of theta y is equal to M, and cos of theta z is equal to N. This is just for, just for writing purpose, not very fancy thing, okay. Now let us try to define the distance between P1 prime and P1. You see, P1 prime is on the source here and P1 is somewhere over here. So if I have x1, y1, z1 prime over here, and I have x1, y1, z1, the distance will be what? X1 prime minus x1 square, y1 prime minus y1 square, z1 prime minus z1 square, whole square root. The distance between P1 prime and P1, right? Now this x1 prime, we have just said that this x1 prime here, from this center, so that is R into L. You see, R into L. This is R into M. This R into N. So I can remove this x1 prime as R into L, R into M, R into N. Correct? So effectively, these distances I am just representing in terms of this theta and R. That is the transformation I am doing. Not doing very much fancy thing. Okay. So there will be this R square here, R square here. So I can take this out. So let's say if I take R out of here, like, so L minus x1 by R whole square, M minus y1 by R, N minus z1 by R is whole square. So if you can do the square, so this L square will be coming from here, L square, M square will be coming from here, N square will be coming from here. Then you will have minus 2 into, correct? Minus 2 into x1 by R, that is L into x1 by R, then M into y1 by R, N into z1 by R, and there will be terms x1 by R square divided by R square, y1 square by R square. Now because R is very large, I can ignore this R square term, right? So that's why I did not write. So now you will get, almost equivalent to something L square plus M square plus N square, which is effectively 1. That is, cos of theta x square plus cos of theta y square plus cos of theta z square. That is actually 1. Okay, mathematically you can show what happened. Okay, yeah. So, so this is 1. So 1 minus 2 by R, L x1, M y1, N z1 whole square root, correct? Now look at this term. This is 2 by R. L into x1, M into y1, N into z1. This x1, y1, z1, these are coordinates on Earth, right? This x1 is the point where we are measuring. Kitna bhi hoga. This will be like, maybe kilometer, hundreds of kilometers. But this R is the distance between the source, right? Minimum parsec to hoga, right? Parsec is like 10 to the power 16, right? Right? So this 2 by R into this number is very small, correct? Because the R is in denominator, right? R is very large and all these numbers are like, in kilometers or so. So you can do a binomial expansion, correct? So 1 minus 2 by R to the power half would be 1 minus half into 2 by R. So the 2 will cancel. So 1 by R into this term. Now 1 by R and this term R will cancel. So basically it will be R minus Lx1, My1, Nz1. This is clear? Right? Okay, great. So this is the distance between P1 prime and P1. Then we will have also the distance between P1 prime to P2 also. Now if you do that, all this x1, y1, z1 will be replaced by x2, y2, z2. That is the coordinate of another antenna. Correct? Now if you do that, so E of P1 is star of P2, I of P1 prime you see this d minus d. Now you see here, if you do this P1, d of P1 prime P1, this one, and P1 prime P2 will be the same thing. And if you minus it, this RR will get cancelled. You will get, L into x2 minus x1, y2 minus y1, z2 minus z1, right? D of, this is clear? Yeah, don't get lost, huh? So I'll just, so this between P1 prime and P1. P1 is my location, antenna location 1. Okay. So this, what I'm getting is R minus L of x1 plus M into y1 plus N into z1. That is what I got, right? Now the distance d for between P1 prime, which is the source, and then P2. P2 is my second antenna, right? So I will get the similar thing, R minus L into, now x2. This x1 was the location of the antenna 1. Now I will get here x2 plus M into y2 plus N into z2. Now if I subtract this guy, these two, this R and this R will get cancelled, this minus will become plus, correct? So L into x2 minus x1, yes, plus M into y2 minus y1 plus N into z2 minus z1. So this is basically d P1 prime and P1, that is antenna 1, minus d P1 prime P2, that is antenna 2. So this is effectively the path difference between those rays, right? D means what? That coming from antenna 1 and this is antenna 2. I am subtracting this two, that is the extra path difference will appear in the phase term. Yes, you see that is appearing in the phase term, that is L into x2 minus x1, M into y2 minus y1, Z into z2 minus z1. Yeah, and this d omega, that is, remember I was telling that you have to integrate over all the sources on the sky. That is the d omega term, and this d omega actually can be written in terms of dl and dm. And this is just mathematical thing. Is, I mean, that solid angle, there's the over which area you will integrate. You are getting this electric field over here that is coming from some part of the sky, right? And you have to integrate because all the electric field from the here and everywhere will come and join here, right? So now you see this terms, this becomes like this. So effectively, whatever I have measured, I measured this thing, right? And electric field in one antenna, electric field in another antenna, multiplying and averaging. And that leads to something like this, right? I is what? I is this quantity, right? This and this, it is I of P1, right? Now this I can say that in a particular direction, L and M. What is L and M? That is theta x, theta y, and theta z, correct? So up to this point, it is fine. Raise your voice if you, yeah. Fantastic, right? Now, what is K? K is equal to 2 pi by lambda, correct? K is equal to 2 pi by lambda. So if I e to the power ik 2 pi by lambda, if I write, this lambda I just push in, it is L into x2 minus x1 by lambda, y2 minus y1 by lambda, and z2 minus z1 by lambda. So this, look at this term, x2 minus x1 by lambda. What does it mean? It means the distance between these two antenna in x-axis in the unit of lambda. How many lambda apart, correct? Similarly, the distance between these two antenna in the y direction in the units of lambda. So I can define this x2 minus x1 as u, y2 minus y1 as v, and z2 minus z1 by lambda is equal to w, right? So if I do that, then this equation becomes e to the power I 2 pi L into U, M into V. I'm just defining it. I mean, this, units, when I'm expressing it in unit of lambda, I just choose to call it U. That's about it. Okay. And N into W and this thing. Now look at this. This, does it, I mean, this equation, does it look familiar? Huh? If you know, don't say it. Does it look familiar? Yes, no, we have not seen anywhere or something. Something e to the power minus I 2 pi. This looks like a Fourier transform, isn't it? You have a function over here, you have a kernel and DL dm. Forget about this part, we can deal with this, okay? Now it does in fact look like a Fourier transform, and if you place this, it actually the equation looks like a Fourier transform, and it does convert into a Fourier transform in two situations, where let's say in one situation W equal to 0, let's say, okay. If W equal to 0, then if you go back to the previous thing, here you see, because here this is DL dm, there is no dW, right? So if you make W equal to 0, so it is become like L into U, M into V, correct? And this will become like this. So this is a Fourier transform relation, okay? And then another point is that if n equal to very small, then if this is very small, close to 0, then also you can actually ignore this term, and again it becomes a Fourier transform relation, right? Now think of this situation, right? What I did, I had electric field from two different antennas, just I have multiplied and averaged, correct? And I have found out that this quantity, we call it visibility. The radio astronomy community call it visibility, this quantity, that multiplication and average. You will get some number, right? Complex number. So that is visibility. It turns out that visibility is basically Fourier transform of this I, which is basically the intensity in the sky, isn't it? We have not done anything fancy. If we can measure the electric field coming from the sky precisely, multiply, do an average, which we call visibility, it turns out that it is the Fourier transform of this intensity distribution on the sky. Now you can do to get I, you can do an inverse Fourier transform. If you can measure this thing, correct? If you can measure this thing, so you can actually do a Fourier transform, inverse Fourier transform, and you can get intensity. That is what we do. In the imaging, you will see that we will, when we perform this T clean task or WS clean task, it is actually doing a Fourier transform. Okay. Now, any Fourier transform relation, if you see, it's a integration from minus infinity to plus infinity. Fourier transform, basically, one part, each component over here depends on all the components on the other side. So it means to get this I, L and M, you need to measure this, visibility at all the UV points, correct? Let us remind what are the UV points. UV point is basically this x2 minus x1 by lambda, right? x2 minus x1 by lambda, and y2 minus y1 by lambda, correct? So it means I have to measure all the UV points. It means I have to keep moving these antennas. This x2 minus x1 is equal to 1, then move this antenna x2 minus x1 is equal to 2, 3, 4, 5, so that I can fill the whole UV plane, right? And that is done in a very fantastic way, which is called aperture synthesis. Okay, so what happens is that my two antenna is on the earth, right? Now my source is very far away. Now if this is my line, I will have some x1 and x2, correct? Now earth rotates. Earth rotating means what? The relative position of this antenna with respect to the source changes. So it means that x1 and x2 also changes, correct? It's basically the projection of these two antenna in the xy plane. So if you rotate it, so these vectors keep changing. So if this keep vector changing, then the projection is x1 and x2, they changes, right? So effectively it means if you keep recording this correlation, let's say after 2 seconds or after every 10 seconds, your antenna position with that source is also changing. So you are effectively measuring this antenna voltage correlation, what is the visibility at different UV points, correct? And this is how, this is called aperture synthesis, and this is how you measure all the UV points. So unlike optical observations, radio observations actually, it's like about 8 hours, 10 hours time. So why? Because you are basically sampling the UV planes, time by time, every time 10 seconds, every 10 seconds, rotating, projection changes, you are measuring different U, different V, different U, different V, right? And if you look at this picture, so this is a UV coverage of GMRT antenna distribution. So that is why if you have only 2 antennas, let's say you have 2 antennas, so these 2 antenna will measure the electric field correlation only once, so to fill the UV plane, you have to do it for a very long time, correct? But let's say you have 30 antennas. Now 30 antenna can make 435 pairs, 130, 12, 19, 92, 97, like that. So 430 pairs, you are recording this voltage, right? So in computer, you can do this correlation individually, 1 to 2, 2 to 5, 5 to 7, like that. So at the same time, in each timestamp, you will get like 435 UV points, correct? And then you go to the next timestamp, another 435, another 435, like that. So this is kind of this UV distribution. As you can see, this is not completely filled, right? It is not continuous. So there will be some imaging artifacts. If you do the Fourier transform of this distribution, this measurement, you will get a sky image. But because Fourier transform, if you see, this is an integration, right? Integration means it has to be continuous, correct? It has to be also from -infinity to +infinity. But you cannot place your antennas at -infinity to +infinity, right? So there will be some limitation, but it does guarantee you that you will get some image. Okay. So now that's all said and good. Now, to convince you guys, I have also made some real examples so that you trust me. Okay. So what is the Fourier transform of a delta function? Constant, right? Here is a source, which is a calibrated source, like a point source. Now, point source is a delta function, right? It is at that point. It is not anywhere else. Now, if you look at the visibility of this guy, how it looks like, this is how it looks like. So this y-axis is basically that E star amplitude. Okay. So that E star, that is the visibility, amplitude of the visibility, that will be constant for a point source, right? Because you see here, this relation, if this is a, this is an inverse thing, right? So if this is a delta function, the inverse Fourier transform of this delta function, here you should get constant. Means even if you change the U and V, the value or the amplitude should not change, right? This is what is happening. So this x-axis effectively is basically square root of U square plus V square. It means the U and V is changing in this direction. Even it is changing in this direction, you see the amplitude is actually constant, right? And this is a real one. This is not, no fabrication has been gone in. Okay. Here, this is another example of this NGC 3741, which I showed in the previous session. So this is a H1 map of that guy, and the UV distribution actually looks like that. This is very difficult, intuitively say, from here to going here. But if you do a Fourier transform, you get this. And the whole radio astronomy imaging actually based on this. But because this sampling of the UV plane is not continuous, and also it is not from -infinity to +infinity, there are some imaging limitations. Okay, and we try to tackle them with different types of algorithms. But the basic principle is this: you have 2 antennas, they act like double slit interferometer, as I explained. You get the electric field, multiply them, and average. That is your visibility. That we will see, and you take this visibility, model them properly, in a sense, do some cleaning on them. That we will come actually in the next session, and do a Fourier transform, and you get your image. Okay. Yeah. So here I'll stop and take questions if you have. Yes. Okay.
Yeah.
Go ahead.
In the southern declinations, the image was not very clear. Why?
Which one? You're talking about this?
This one, yeah.
So basically what happens is that, let's say I have a source, okay, which is right at the top of my head. Now that source will see my full baseline, right? It's like that, two antenna sitting here. Now earth is rotating, this in projection, it is X is shortening. But what happens if it is not at my head, it's at the horizon, right? It's like this. I have this earth, correct? The source is somewhere here, correct? Earth is rotating like this. So in this projection, this will change, correct? This will change like this. But what if the source is sitting over here? It will always see like, same U and V, okay? It means even the earth is rotating, the U and V will not change as much. So that is why you see, these tracks are actually not kind of, so look at this track, it actually covers from this U to this V, again come back over here. But here the range is actually different. So this declination is minus 45 degree. So GMRT has a declination. So GMRT
it mostly depends on the location of my antenna.
Yes.
Right?
So it is mostly depends on location of your antenna and which source you are looking at. Okay. If the source happen to be, top of your head, is fantastic. But all the sources are not like that. The source might be very much, down. So there you will have this kind of problem, and you will also have problem in imaging also, because the UV plane is not properly sampled. Yes.
Can you go to the slide where you multiply EP1 into E star P2?
Yes.
Previous slide. No, sorry, the next same slide. Same slide. Yeah. The second last equation. So what is that D square here?
This is basically the distance.
There are this P1, P1 dash P1 and P1 dash P2. So
yes. So basically, P1 dash P1 is the distance between the source and the first antenna, and this is source and the second antenna. Now these two distance, there is a minute difference, right? But when I am talking about the amplitude term, I can say that they are almost same.
Yeah.
That is D square. But phase you cannot do, because phase changes in every lambda. That is why I have calculated down all this complicated stuff, by subtracting and the L into X. In fact, you can do that calculation and multiply this D1 into D2, but that is effectively will be D square only, not a problem.
I have one more doubt.
Yes.
So it's a very basic doubt regarding the array interferometer. Can you go back to that slide? That picture of the VLA.
Yes.
Yeah. So you were saying that if there is a large dish, we use pieces of the dish and then we can create some antenna.
Correct.
So just I had a question that these particular antennas, the curvature of these antennas will be similar to that dish if we are assuming something like this, and again the height of the antenna at different points.
No. See, here, what this guy do? This is effectively the rays is hitting over here and coming over here, right? And here you are basically adding this electric field coming from this ray and the electric field coming from this ray. You are just adding them in phase.
Oh yeah.
Instead of that, I have one antenna over here which is measuring this guy, another antenna over here which is measuring that thing. I'm just adding in phase, and all these phase thing you can manipulate in computer, not a big deal, right? So you can make them, you can adjust the delay such a way so that they act like a parabolic disc if you want to add them in phase.
Yeah, makes sense.
Huh? Anything else? So if not, so let us break for tea.